Hey guys, in this video we'll be using the Jacobi method to find the solution of linear systems by the iterative principle, and we'll be doing this in C++. Before we get into the actual implementation, I will explain the actual concept of how this method works, and after that we will proceed to the actual implementation in C++23. Before we get into the explanation, I would like to explain some of the prerequisites for this method. The first one being the most important, that is the matrix A should be diagonally dominant. What does that mean? So it means that in each of the rows, the diagonal element corresponding to that row must be greater than or equal to the sum of all other values. So we are taking absolute values here, okay, just keep that in mind. So for here we have these green dots. The green dots represent the diagonals, and this pink stuff represents the other elements. So when we take this first row, we want this green diagonal element to be greater than the sum of these two, right? So that's what I have written in this. So that condition should satisfy for all the rows, and if any one of the diagonal element is less than the sum of the other elements in that row, then it is not diagonally dominant. So that means we cannot do this Jacobi method. Then the next one is we need to provide a guess for the values that we are finding. So suppose the formula is ax is equal to b, right? Now we provide a guess for x. Generally we put 0 as the guess, but we can fine tune that to actually affect the output. And then the third one is the tolerance. So this is like the stopping condition for the algorithm. This is like the amount of tolerance we are accepting for the accuracy, like how close we want it to the actual result, because Jacobi method is actually just approximation of the actual value. We are providing the user a opportunity to adjust the tolerance so that they can fine tune the result, right? So how close it gets to the actual value. So we need to provide a tolerance value. In the implementation we are defaulting that to something like 0.001, or we can increase the sensitivity of this. It doesn't matter, it will give the answer anyway. Let's get into the equation. Now this is the equation for the Jacobi method. For a matrix A and the right hand side matrix B, we need to find a matrix X that satisfies this equation. So this is the actual outcome of almost all of the linear system stuff related to numerical analysis. The stuff we did in the first video, that is Gauss elimination, the second one LU decomposition, all of this finds the X matrix. So in this case, this is the equation. It seems kind of very hard, right? But it is super easy. I will explain that. So x k plus 1, so this is the kth iteration. Remember, this method is iteration, right? Like it's like loops, right? So this is the k plus 1 result of x, and this is the kth result of x. So initially k is equal to 0, and first I said that the initial guess would be default to 0 by choice. So here x0 would be 0 0, stuff like that. Alright, so that is the initial guess. From this we find a value that is x of 1, and we plug that back in here and we repeat the process. And what does this all mean, the other stuff? So D inverse is like the inverse of diagonals. This B is this one, and this L plus U I will explain. So this is the basic equation. Now over here I have explained the individual components. This B is self-explanatory, and this D dash is the inverse of the diagonal only matrix. So this is the diagonal only matrix, right? And we take the inverse of that. This is the D inverse. And what is this L plus U? L plus U is the part of the matrix where we replace all the diagonal elements with 0. Like imagine there is zeros all this way. So that is the L plus U matrix. And also remember that if we add these two matrices, that is the diagonal matrix and the L plus U matrix, we get the original A matrix. So that's the concept. Now when we run this equation, we need a stopping condition, right? Because if we don't provide that, it is going to run indefinitely. We don't want that. That is where the tolerance comes in. So this is the area where we decide where to stop. The first option is to give a max iteration variable. So this is something like 10,000 something. We can adjust that. We can add more zeros if we want, but this is like the upper limit. We don't want the equation to run more than this. So this number is heavily dependent on the system that we are running on. And the next important part is tolerance. So this is where we can actually fine tune the algorithm. So this is the equation for tolerance. So you might have seen this notation. So this means the norm. So here we multiply this x value that we found here. So suppose this is the kth value of x. So we multiply the value of x we get here with the A matrix, and we subtract the B matrix from that, and from that we get a vector, or we actually convert that to a vector, because this B has order of, like, it has one column and n number of rows. So this is basically a vector. So we get a vector output and we find the second vector norm. So that basically means the magnitude of the vector, and we get a scalar value and we check if it is less than the tolerance that we provide to the function. If it is less than the tolerance, we exit out of it and we return whatever we got out of this xk matrix. So this is the final answer. Now let us get into the actual implementation in C++23. Here is the implementation for the Jacobi method in C++23. So I have created two matrices A and B. So this is like the question, and we find the answer, that is the X matrix. So we print the matrix A and B, and importantly we check if the matrix A is diagonally dominant, because it is one of our prerequisites. So if we go into this function, we find that it is actually quite intuitive. We check if it is a square matrix, and then we take the sum of the elements except the diagonals, and if the diagonal is less than the sum, that means it is not diagonally dominant and we cannot proceed, and we return out of this main function. And then comes the interesting part. We make the initial guess, that is the X matrix. So we put all zeros inside that for this case. This is where we can actually fine tune the values to achieve the result faster. Now there could be a question, why are we making this X matrix, actually this looks like a vector, right? Why are we making this two-dimensional? Because we are doing matrix multiplication and stuff like that further into the way. And then we pass all these parameters, A, B, initial guess X, and then the tolerance value. And in this function there is also a parameter for the maximum iterations. It is default set to 10,000. Now if we go into this function, you will see that we are finding all of these components step by step. So recall the function that we need. X of k plus 1 is equal to d inverse times b minus l plus u times x raised to k. Now x raised to k, the kth value of x. Alright, so I will put the photo somewhere so you can recall that. Alright, so first we need to find the D matrix. So what is D? D is the diagonal matrix. So we get the diagonal elements and put this inside this two-dimensional matrix. Then we need to find the inverse. Here comes, this is like the one of the complex parts of this program. We need to find the inverse. How do we find it? One of the ways is to use LU decomposition. We can convert this to we can convert one matrix into two, lower triangle and upper triangle, and from those we can do different operations and find the inverse. So here we have two functions. If we go into this first one, we made that in the previous LU decomposition video. It is very not that hard. You can refer that video, I will link that. And then we find the inverse from the LU matrix. So if you go here, it is just simple stuff. We do forward substitution and we take the result and put that inside this backward substitution. If you watch the first video in the series, that is Gauss elimination, we use this same method for finding the values of the linear system without any of the iterative methods. So if you have any doubts, you can refer that. Now from this we find the inverse of the matrix, that is D inverse. So one part of the equation is done. Now we need the L plus U part. What is L plus U? L plus U is the part of the matrix where all the diagonal elements are 0. So we simply set that to 0 like this. And then we need to multiply these two matrices together, because we are separating this function into two parts because there is a minus in the between, right? So we put we multiply this first D inverse with the first part, and we take the second part and separately multiply the D inverse. So we get like two different steps, and we can add them together at the end instead of it's one of the ways you can do it directly as well. I thought this would be easier. Okay, so we multiply D inverse and L plus U. We have a helper function, matrix multiply and scalar matrix multiply, because we need a minus here, so we need to multiply it with minus 1. So I will quickly show that. So this is the matrix multiply function. I just copied it from Stack Overflow. Okay, and then we have the scalar multiply function. It is also very simple. We multiply all the values with the scalar we provide. Alright, and then we need to multiply the inverse with the B matrix. This is the second part of the original equation. We simply put the inverse and B inside that. Now comes the iterations. This is very interesting. Now we need to put the x stuff inside this. Wherever we have x, that means it comes inside the iteration part. Alright, so we need to multiply the first expression with the guess. So initially it is 0, right? X of 0 is the initial guess. We multiply that, and in expression 4 we add this expression and this expression together. So it all comes together into a final value, that is the x. Now what? Now I will skip off this part for now. I will explain that in a moment. So we have x set here, right? So this becomes the next guess, and it comes here, goes to the next loop. If it is less than the iteration, we do this stuff again and again until we reach this condition. So what? So we get the result somewhat accurate to 10,000 iterations, right? Yeah, so that's one way to do it. That's like one way to stop this program. Then the better way is to use tolerance. So that's what we do here. This is also very simple because we have the equation ax minus b. We find the norm and we check if it is less than the tolerance value. We need to find the ax expression. What is ax? Ax is simply multiplying the A matrix and the X matrix. Simple as that. Then what? We need to get the negative value of b, multiply it with minus 1. And we need to add these together. Remember, subtraction is just addition with a minus sign to the second variable or something. So ax minus b is just adding these two together. And now to find a vector norm, because this is a matrix, remember, this is a vector of vectors. We need to convert it to a single vector. To convert that, we use the views transform from C++. It is like 23 or something. We get the first element because it is a one column vector, and we convert that to a one dimensional vector. And from this we use the find vector norm method that we made in the previous video in vector and matrix norms. I will also link that up here. And we take the second norm, that is basically the magnitude, and we check if this residue is less than the tolerance. If it is less than the tolerance, that means we have reached the end condition. We can stop this function and we break out of this loop. Now what? Now we return this x. That is what we found here, and we return that over here and we print the matrix. Now let's try running this. Now let us try to run this program. I will use this script I have made. So here is the A matrix, here is the B matrix, and it has solved this value and we get the approximate result. because we set the tolerance as 0.001, you will notice that after 3 or 4 numbers, the result kind of scrambles out. See, it's like 1.999 and then 589, something like that, right? So the actual values are 1, 2, -1 and +1. So you will see the values are pretty close to the actual values we need. And now we can actually verify this result by putting it in some calculators online. I will show that now. Now I will run this. Yeah, we get the answers 1, 2, -1 and 1, and that is the almost same as we get here. Because they are using Gauss elimination, we are using approximation by Jacobi method. So we get a near value. Now if we try to increase the number of zeros, like somewhat here, and run that again, we will get a much better result. Let's add more. See, we get 1, 2, -1 and 1. So yeah, this is the implementation of Jacobi method in C++. So yeah, I will see you in the next one.